Applying Newton's laws. In this video, you will learn how to apply Newton's laws of motion to a static equilibrium situation, in which an object is at rest or is moving at a constant velocity, and also to a non-equilibrium situation in which there is an acceleration. Before working on this video, obviously you will need to know very well what Newton's laws are. If necessary, you should refer to the following video which covers this topic. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. The most important thing you should learn to solve the following problems is knowing how to translate a sketch of a situation into a free body diagram with appropriate axes so that Newton's laws can be applied. Let's start from the simplest to the most complicated situations. One block of mass 4 kilograms is on a frictionless horizontal table. A force of 10 newtons is applied horizontally on it. Find the acceleration of the block as well as the normal force. Make a diagram and identify the forces acting on the body. Earth pulls the block downwards with the gravitational force, which we call weight, and has a magnitude equal to mass times gravity. Then the block pushes the table downwards as well. The table reacts and pushes the block upwards with a normal force. The normal force is exerted by the table and is perpendicular to the interface between the table and the block. It points upwards in reaction to the downwards force that the block exerts onto the table. The downwards force from the block onto the table and the upwards force from the block onto the earth are not shown since these forces are not exerted on the block. At last, one force pulls the block to the right. Here we could draw the force both to the right and to the left. Draw a free body diagram. Remember that in a free body diagram, any object is represented as a point of mass m at an xy coordinate system. We can now apply Newton's second law in each direction. The resultant force in the y direction is the sum of the weight and the normal force. As the box slides horizontally across the table, it does not move vertically. This means that the resultant force in the y direction is zero. Thus, in the y direction, the magnitude of the normal force is equal to the magnitude of the gravitational force. In other words, the normal force cancels out the weight. The signs of the components must be consistent with the axis direction, thus the weight is negative. The resultant force in the x direction is the sum of all forces in the x direction. But in the x direction there is only one force, which is F. The resultant force is mass times acceleration. Therefore, the acceleration is 2.5 meters per second squared. A constant horizontal force of magnitude 20 newtons is applied to block A of mass 4 kg, which pushes against block B of mass 6 kg. The blocks slide over a frictionless horizontal surface. Find the acceleration of the blocks and the horizontal force on block B from block A. Make a diagram and identify the forces acting on each body. The weights of the two blocks act at a right angle to the horizontal and push the surface down. The surface reacts and pushes the blocks up. Some object applies the F force to block A. Block A pushes block B to the right, and the block B responds and pushes the block A to the left. FAB, the force on block A due to block B, and FBA, the force on block B due to block A, form an action-reaction pair. For each body, draw a free body diagram. Add an XY coordinate system. We can now apply Newton's second law in each direction. Because the blocks do not accelerate vertically, the weights of the two blocks are cancelled out by the upward forces of the surface on them. This means that the resultant force in the y direction is 0. Block B is accelerated by FBA and block A is accelerated by the resultant force F minus FAB. Do not forget that the forces FAB and FBA form an action-reaction pair, so they have the same magnitude. Solving these equations for A by adding the two equations, we get the acceleration. We now use this acceleration to get the force acting between the masses. A box of mass 80 kg is to be pulled along a frictionless horizontal surface by means of a light rope. The rope is pulled with a force of 100 Newton and the rope is inclined at 25 degrees to the horizontal. Find the acceleration of the block and the normal force. Make a diagram and identify the forces acting on the body. The weight of the box acts at a right angle to the horizontal and pushes the surface down. The surface reacts and pushes the body up. The rope applies the tension force to the box. Draw a free body diagram. Add an XY coordinate system. And find the components of the tension force. We can now apply Newton's second law in each direction. Because the blocks do not accelerate vertically, the resultant force in the y direction is 0. Therefore, the magnitude of the resultant will be equal to the magnitude of its x component. Solving this equation for A, we get the acceleration. In the y direction, we know that the resultant is 0. So we solve this equation for n. A block of mass 8.5 kg is tied to a cord on an inclined plane as shown below. Find the tension in the cord, the normal force acting on the block, the acceleration of the block when the cord is cut. Make a diagram and identify the forces acting on the body. The direction of the weight is straight downward, but the direction of the normal force is perpendicular to the surface. The rope applies the tension force to the block. We draw a free body diagram and add an XY coordinate system. When we are dealing with inclined plane, we take axes parallel and perpendicular to the surface and resolve the weight into x and y components. We find the components of the weight. We can now apply Newton's second law in each direction. Because the block is at rest, the resultant in the perpendicular direction to the surface is 0. and the normal force is equal to the perpendicular component of the weight. The resultant force in the parallel direction of the surface is zero as well. So we can solve this equation to get the tension force. When the rope is cut, the tension force does not act on the block and the block slides down. In this case, the resultant force in parallel direction of the surface becomes the component of the weight in this direction. So we apply the second Newton's law to get the acceleration.